Hey there, my name is Stefan Pham. I work for Fraunhofer Focus, and I have the honor of presenting the CMSD standard to you. This was joint work together with Will Law, chair of the CMSD standard, as well as Ali and Bertrand from Broadpeak, besides my colleagues from Fraunhofer Focus. I will go over an update of current implementations of CMSD, as well as two use cases that we had time to evaluate. So first of all, CMSD stands for Common Media Server Data and was standardized in a pretty short amount of time and was published just a couple of months ago, November 2022, as part of the CTA Wave group. It is a uniform method for media servers to exchange data with each media object response, so basically dash HLS segments. And the aim is to enhance distribution efficiency, conformance, and ultimately the user experience. On the right-hand side, you can see examples of CMSD parameters. As part of this presentation, I will highlight two attributes specifically. One is the MB attribute, which stands for maximum bit rate, and the other one is ETP, estimated throughput. Both are currently implemented, integrated into the open source Dash.js player. And on the server side, on the origin side, basically there are two implementations. One is from Unified Streaming. The other one is from University of Singapore and ASEAN University. There's a counterpart to CMSD. It's been mentioned a couple of times already today and yesterday. This is basically client-to-server communication, CMCD. This was specified, also chaired by Will Law, before CMSD. It's basically player metrics being sent from client to server. And on the other hand, CMSD can take these client metrics to give information, control client behavior to some extent. Besides that, CMCD can be used for quality of service monitoring, streaming analytics in general, and as usual, improve the overall quality. CMSD can be transported in two ways. You can either add custom HTTP headers, or you add query arguments to the URL. It is also possible to send it as independent JSON objects. This is also integrated into Dash.js. There are example players Daniel showed yesterday already. There's a blog post on that as well. On the right-hand side, again, you can see examples of CMCD parameters. For example, the current buffer length of the player, current bitrate, which segments are being requested next, etc. So information that the CDN, the edge servers, can use to optimize the streaming session. So how is CMSD data transmitted? Again, simple approach using HTTP response headers. So with each object request that a client is sending, the server can append HTTP headers to the response. And there are two types of CMSD parameters that can be used. There is CMSD static. As the name suggests, this is static information. And as you can see in the example below, there's something, an example for static information would be the object type, whether it's audio or video. In this example, it's a video. It also mentions the streaming format. In this case, it's HLS, could be Dash as well. The stream type, is it a VOD or live stream? So static information that doesn't change throughout the streaming session. In this example, we also have a duration of the stream, the current bit rate and an identifier of the CDN or region currently being streamed from. And then there are a couple of dynamic attributes in this example, and I highlighted in yellow here the two attributes which we will go over in this presentation. One is the ETP. Again, this is the estimated throughput being calculated on the server side within the edge. And then the other yellow highlighted attribute is the maximum suggested bit rate, in this case 5,000 kilobit per second. So I'm going back a couple of years. The concepts are very similar to what was standardized within MPEG-Dash Part 5, also called SAN, Server Network Assisted Dash. We did a couple of implementations back then, like sending metric data from client to server. You can see that on the right-hand side, that's the metric messages being sent. So this is very similar to what is being done in CMCD. Probably a bit more efficient than sending XML objects from client to server, if you're familiar with the MPEG SAN standard. And on the other hand, the SAN standard also enabled use cases similar to what CMSD is doing. In this architecture, it's the DANE block in the middle, dash-aware network element, which is sending certain messages from server to client. For example, suggesting a maximum bit rate. This use case was called shared resource allocation in SAN. Just going back in history, because back then we were also thinking about use cases for SAN shared resource allocation. This could be use cases where the Wi-Fi access point or the mobile network has certain constraints in terms of bandwidth. So this could be in a sports stadium where video content is streamed to devices which are all connected to the same bottleneck. It could be in airplanes, people streaming video, in trains, or simply in home networks. Could theoretically also be CDNs, which, let's assume, we've been talking about content steering all day. Let's assume even the other CDNs that I could steer to are overloaded. Then it is possible for the CDN or edge servers to lower the bit rate on all connected clients. In the case that I'm not even able, or in the case that other CDNs are overloaded as well. So the goal of this shared resource allocation use case, which is similar to the suggested maximum bit rate in CMSD, is controlling the available bandwidth and ideally also using it optimally. SAN also came up with different strategies how to distribute the available bandwidth to clients. The simplest one was called everybody served. Simply use the available bandwidth divided by the number of clients and fairly distribute it among them. There was something else called premium privilege, where you had like prioritized clients which first got the highest available bit rate, and then the rest was distributed to the other clients. And this is the setup that we used back then, and we kind of set this up again recently, updated it using or integrated latest -JS. We integrated CMCD for the metric reporting. And it's basically we're using Raspberry Pis, run Chromium browser on it. Each Pi is able to handle 2 Chromium instances. And we throttled the bandwidth for, in this case, 12 Pis times 2, 24 clients, and used a simple bitrate ladder, in this case, 500 kilobits to 5 megabits. And In this case, we just let them stream. We started them sequentially, and what happens is when you do that without controlling the available bandwidth is, since the clients are not aware of each other, they start, and this is what happens in adaptive bitrate streaming, they try to get to the highest available bitrate, and they essentially compete against each other. So it becomes this oscillating behavior or aggressiveness among the clients. There's been many papers on this in the past few years. And this, of course, becomes worse with increasing bandwidth requirements. We talked about higher frame rates today, Ultra HD. So what you can see in the graph on the right-hand side, all the colored lines are sessions from each of the pies that we started. And we are basically plotting the representation switches of each client. And you can see it's switching up and down, causing bad quality of experience. Let's see if this works. This is a short video. You can see that in action as well. We're starting the different clients sequentially, and they start switching up and down a lot, which again is bad user experience. So how do we solve this behavior? We use the CMSD MB, suggested maximum bitrate attribute. In this case, we use the simple algorithm, which is basically looking at the available bandwidth and dividing that by the number of clients. And that value we are sending with each segment response. So we set the HTTP header. Dash.js is aware of this MB attribute, and it then internally sets this value and then picks basically from the encoding ladder a bitrate which is below the suggested maximum bitrate. In this specific test run, we had 60 megabit per second for 24 sessions. Simple math leads to 2.5 megabits. In the encoding ladder that we had available, there was a 1.8 representation. So you can see that in the end, they, like on the right-hand side of the graph, you can see they are staying at 1.8 megabit in the end. The other use case that I wanted to present to you is the ETP attribute. What can be done with that? It stands for estimated throughput. One idea would be to improve the selection of the initial bit rate with the ETP attribute. So usually adaptive bitrate clients take, let's say, the last 3 segments that were downloaded and estimate the throughput based on that. But if you're at the beginning of the stream, you don't have that information. So that's something where ETP could be used to select a more appropriate bitrate for the client at the beginning of the streaming session. The other one, and this was contributed by Broadpeak to the short paper that we submitted for this conference, is using server-side throughput information for low latency streaming using chunk transfer, for example, using CMAF. Client-side throughput estimation is challenging, so why not estimate the throughput on the server side? And the following graphs show the evaluation. This was also mentioned in the paper, and there are a couple of white papers mentioning the improvements as well. What you can basically see in the bottom graph is the dark blue line is the estimated throughput, which is always overestimating the available bandwidth. This leads to basically buffer underruns. That you can see on the top graph. Whenever the red line drops to 0, that's a buffer underrun. The green line is the playback rate, which also drops to 0, which basically means stalling. This is based on the L2A algorithm built into Dash.js. And essentially the same thing happens to the other algorithm built in, which is based on MOV parsing throughput estimation on the client side. Again, dark blue line in the bottom graph shows overestimating of the bandwidth. So that means the client is basically downloading higher bit rates than it's able to sustain. And again, leading to buffer underruns. Last but not least, and that also concludes my presentation, is the throughput estimation based on ETP, so done on a server side. And you can see this is much more accurate and basically avoiding buffer underruns. Player is able to keep the playback rate and also live delay. Thank you very much for listening.
Okay, thank you.